let me say something about Quaternion integers, something Hurwitz was working on in 1919. He made a whole course about this, and I read a little bit in his booklet. It's gorgeous. There's a lot of interesting number theory, also classical number theory involved. So first of all, the quaternions, this is just R4, four-dimensional space, but he has an algebra structure, which Hamilton famously found, right, while walking over this bridge in Dublin. Euler already knew that this multiplication satisfies this identity. It's an identity for squares, and so the norm multiplies, and this implies immediately that we have a division algebra. We can the inverse is just explicitly given, like in the complex numbers, as a conjugate over the norm. So everything is explicit, and the interesting thing is this is the only complete associative non-commutative division algebra according to these theorems of Frobenius or Hurwitz. And interesting are the units, very beautiful. The units are the unit quaternions. This is SU2, it's a three-dimensional sphere. This is the Hopf vibration of the three-dimensional sphere. Very beautiful part. And then we have also, in the quaternion integers, there's a finite group of units. And these units there are 24 elements. And if you draw them in space and project them into 3 dimensions, this is what I printed here. You have the 24 cell. 24 cell is a self-dual platonic solid in 4 dimensions, and it's like we have 5 platonic solids in 3 dimensions, and we have 6 platonic solids in 4 dimensions. Afterwards, only 3. But Schläfli found that out, and so that this 4-dimensional space is somehow the most symmetric one. It's a self-dual, very beautiful geometric structure. So there are 24 cells, 24 vertices, there's duality, 96 edges, 96 triangles. So very beautiful structure. Hurwitz talks a lot about the inner symmetries. So first of all, he looks at the inner symmetries of the quaternions and then the inner symmetries of the integers, and that's why he's led to this notion of half integers. He needs half integers to have a natural number theory, and that was later then by Emmy Noether was kind of make a whole theory about non-commutative rings. So we have to we can say what is an order, and that's a maximal order, and so it's kind of a very natural number theory. And in that in these integers we have units, and these units we have just said it's this. It's also a group. This is a subgroup of SU2, and it's the binary tetrahedral group. So I thought first, that this is also the symmetry which you have of all the integers. But it's a little bit surprising, as Hurwitz has pointed out already, there's a larger symmetry of inner automorphisms in the integers. For every n, for every integer n, you have always a quaternion with norm n. That's the Lagrange 4 square theorem. And now for primes especially, we have p is a prime, then by this formula here. So if the norm is a prime, we cannot factor it. We have really a prime also in the quaternions. And Hurwitz looked how many primes are there above a rational prime, and he gave the formula 24 times p plus 1 in the case of an odd prime. In the case of an even prime, and that's kind of the interesting thing, then we have 24. And I drew this here. Actually, I printed it overnight here. This is the, again, 24 cell, but here this represents all the even primes in the quaternions. So even primes in the quaternions is like 1 plus I, or 1 plus j, 1 plus k, or I plus j. So there are many of them, and there are just everything is generated by taking one of them and then multiplying it with a unit. And then 24 units, so there are also 24 here of this. So the formula here is then this is even n, so we have not this Jacobi formula for the number of ways you can write the number as a sum of 4 primes, but then we have in the case n equal to 2, we have just 24 cases. I like to think about all this also in the context of particles, right? You can look at the primes and you can put them into the region where the coordinates are ordered, a smaller equal to b smaller equal to c smaller equal to d, and all non-negative. And then you can look at you have less primes to worry about. Like we have, for example, already in the case p equal to 3, we have 96 primes. So there are lots of kind of just changes of, permutations and changes of signs. So they are not very, this is not very insightful. It's much better to put them just into that region Q, and then for 3, we have just 2 primes in that region. One of them is a Lipschitz prime, it's 1110, and the other one is what I call a Hurwitz prime. So these are both quaternion primes. This is one Lipschitz and one Hurwitz prime. There's a unit which maps this to this. So they're equivalent. And so kind of the association is to see them as 2 quarks which are forming a meson. And the association comes from, because in general what you have for any prime, you have either a baryon, kind of 3 quarks together, or you have a meson, and p equal to 19 is a case where you already have 1 meson and 1 baryon. And if the primes are getting larger, then you have more such particles. Maybe also something which Hurwitz already did in his booklet is prove essentially unique prime factorization. This has been refined later, especially in the book of Conway and Smith about quaternions, octonions. And the simplest way to state that, we have a quaternion integer. So quaternion integer, and then z decays into primes. So this is not as unique as in the case of rational primes, but it's essentially unique. So what you have in the rational primes, you have uniqueness if you order the primes. You can order the primes, and then you have uniqueness, right? So you can, even if they are the same, 2 times 2 times 3 times 3 times 3 times 5 times 7, you can order them, and you have then unique prime factorization with this assumption. This is no more true in the case of quaternion integers, because there are different ways, more interesting ways, how you can shuffle this. One of the ways is the unit migration. So what you can do, which already Hurwitz knew, what you can put in, you can just put a unit and then an inverse of the unit, and you just put them in, and then you get new primes, right? You can take that, and because of the non-commutativity, this is not trivial. And then you can also look at meta commutation. You can also do recombination in the case if they are primes have the same rational norm. That's what I wanted to say today.